Fiction of the mind. How had Leibniz heard about Newton and Newton's unpublished work? It was not difficult. Word of Newton's discoveries had been leaking out for years. In 1969, in 1669, Isaac Barrow, hoping to promote his young protege, had sent an anonymous copy of the analysis to a man called John Collins, a mathematical wannabe and impresario. Collins had put himself at the group of correspondence New York involving British and continental mathematicians. He was floored by the results in the analysis and asked Barrow how its author was. With Newton's permission, Barrow unmasked him. I am glad my friend's paper I glad my friend's paper give to you so much satisfaction. His name is Mr. Newton, a fellow of our college and very young, but of an extraordinary genius and proficiency in these things. Collins was never someone to keep a secret in confidence. He teased his correspondents with snips of the analysis and wowed them with Newton's results without explaining where they came from. In 1675, he sold Newton's power series for the inverse sine and sine functions to a Danish mathematician named Georg Bohr, and he in turn told Leibniz about them. Leibniz sent a request to the secretary of the Royal Society of London, a German-born schmoozer and promoter of science named Henry Oldenburg. Since I say he Bohr had brought us these studies, which seem to me to be very ingenious, the latter series in particular having a certain rare elegance, so I shall be grateful, illustrious sir, if you will send me to the proof. Oldenburg passed the request along uh, alo- passed the request along to Newton, and Newton was not pleased. Send the proof? Ha! Instead, he replied to Leibniz, though Oldenburg, with page after page of cryptic, intimidating formulas, the full armament of the analysis. Outside of Newton's inner cycle, no one had ever seen math like this, and for good measure. Newton stressed that the material was old hat. I read rather shortly because these theories long ago began to be distasteful to me to such an extent that I have now refrained from them for nearly 5 years. Undeterred, Leibniz wrote back and poked Newton, hoping to extract a bit more. He was a newcomer to all this, a diplomat, logician, linguist, philosopher. He'd only recently become interested in advanced mathematics. He'd spent time with Christian Huygens, the leading mathematical mind in Europe, to get up to speed on the latest developments. After just 3 years of study, Leibniz had already outpaced everyone on the continent. All he needed now was to figure out what Newton knew and what he was withholding. To pry information out of Newton, Leibniz tried a different tack. He made the mistake of trying to impress him. He produced some of his own works, in particular an infinite series he was proud of, and offered it to Newton, ostensibly as a gift, but actually as a signal that he was worthy to receive the secret. Newton replied, though Oldenburg 2 months later, on noted 24, 1676. He opened with flattery, called Leibniz very distinguished, and praising his infinite series, saying that it leads us also to hope very great things from him. Were these compliments meant to be taken seriously? Apparently not, for the next line burned with acid sarcasm. The variety of ways of which the same goal is approached has given me the greater pleasure, because three methods of arriving at series of that kind already become known to me, so that I could scarcely expect a new one to be communicated with us. In other words, thanks for showing me something I already know how to do three other ways. In the rest of his paper, Newton toyed with Leibniz. He revealed some of his own methods for infinite series, explaining them in the pedagogical manner one would use to lecture a school child. Fortunately for posterity, these parts of the letter are so clear that we can understand exactly what Newton had in mind. But when he got into his most precise positions, the revolutionary techniques of his second track on Calculus de Methodis, including the fundamental theorem, which had not leaked out yet, Newton's gentle exposition came to a halt. The foundation of these operations is evidently enough, in fact, but because I cannot proceed with explanation of it now, I have preferred to conceal it thus. On this foundation, I have also tried to simplify the theories which concern the squaring of curves, and I have arrived at certain general theorems, and with that encrypted code, Newton dangled his cherished secret in front of Leibniz, essentially telling him, "I know something you don't, and even if you discover it later, this cryptogram will, will prove I knew it first."
What Newton did not realize was that Leibniz had already discovered the secret of his hand. In the twinkling of an eyelid, between 1672 and 1676, Leibniz had created his own version of calculus that Newton responded and proved the fundamental theorem, recognized its significance, and built an algorithmic system around it. With its help, he wrote, he'd been able to derive in the twinkling of an eyelid nearly all the theorems about quadratures and tangents known at the time, except for the ones Newton was still hiding from the world. Leibniz wrote his two letters to Newton in 1676, nosing around and asking for proofs. He knew he was being pushy, but he could not help it. As he once told a friend, "I feel myself burdened with the deficiency that counts for a good deal in this world, namely, that I lack polished manners and thereby often spoil the first impression of my person." Skinny, stooped, and pale, Leibniz might not have been much to talk, might not have been much to look at, but his mind was beautiful. He was the most versatile genius in a century of genius that included Descartes, Galileo, Newton, and Bach. Although Leibniz found his calculus a decade after Newton did, he is generally considered its co-inventor for several reasons. He published it first in a graceful and digestible form. He couched it and carefully designed elegant notation that's still used today. Moreover, he attracted disciples who spread the word with evangelical zeal. They wrote influential textbooks and developed the subject in luxury and detail. Much later, when Leibniz was accused of stealing calculus from Newton, his disciples defended him vigorously and counterattacked Newton with equal fervor. Leibniz's approach to calculus is more elementary and, in some ways, more intuitive than Newton's. It also explains why the study of derivatives has long been called differential calculus, and why the operation of taking of a derivative is called differentiation. It because in Leibniz's approach, concepts called differentials are the true heart of calculus, derivatives are secondary and are the thought a later refinement. Nowadays, we tend to forget how important differentials were. Modern textbooks downplay them, redefine them, or whitewash them away because they are gas infinitesimals. As such, they are seen as paradoxical, transgressive, and scary. So just to be on the safe side, many books keep infinitesimals locked in ethic, like Norman Bates' Mother in Psycho. But they're really nothing to be afraid of, really. Let's go meet Mother. Infinitesimals. An infinitesimal is a hazy thing. It is supposed to be tiniest number you can possibly imagine that isn't actually zero. Marxically, an infinitesimal is smaller than everything but greater than nothing. Even more paradoxically, infinitesimals come in different size come in different sizes. An infinitesimal part of an infinitesimal is comparably smaller still. We could call it a second order infinitesimal. Just as there are infinitesimal numbers, there are infinitesimal lengths and infinitesimal times. An infinitesimal length is not a point, it's bigger than that, but it's bigger than that, but it is smaller in length you can envision. Likewise, an infinitesimal time interval is not an instant, not a single point in time, but is shorter than any conceivable duration. The concept of infinitesimals arose as a way of speaking about limits. Recall the example in chapter 1 where we look at a sequence of regular polygons starting with equilateral triangle and a square and proceeding upward to pentagons, hexagons, and other regular polygons having more and more sides. We noticed that the more sides we considered and the shorter we made them, the more the polygon began to look a circle. We were tempted to say that a circle is an infinite polygon having infinitesimal sides, but bit our tongues because the notion seemed to lead to nonsense. We also found that if we chose any point on the circumference of the circle and look at it under a microscope, any tiny arc containing that point looked straighter as the magnification increased. In the limit of infinite magnification, the tiny arc looked perfectly straight. In that sense, it really does seem helpful to think of the cycle as an infinite collection of straight pieces and therefore as an infinite polygon with infinitesimal sides. But Newton and Leibniz used infinitesimals, but while Newton later disavowed them in favor of fluxions, which are ratios of first-order infinitesimals and hence finite and presentable, just like derivatives. Leibniz took a more pragmatic view. He did not fret about whether they actually existed. He saw them as useful shorthand, an efficient way to recast arguments about limits. He regarded them as helpful bookkeeping devices that freed the imagination for more productive work. As he explained to a college, philosophically speaking, I no more believe in infinitely small quantities than in infinitely great ones,
that is infinitesimals rather than infinite tuples. I consider both as fictions of the mind of succinct ways of speaking appropriate to the calculus. And what do mathematicians think today? Do infinitesimals really exist? It depends on what you mean by really. Physics tell us infinitesimals don't exist in the world, but then again neither does the rest of mathematics. Within the ideal world of mathematics, infinitesimals don't exist in the real number system, but they do exist in certain non-standard number systems that generalize the real numbers. For Leibniz and his followers, they existed as fictions of the mind that come in handy. That's why the way we will be thinking about them. The cube number, the cube numbers near 2. How to see how eliminating infinitesimals can be? Let's start very concretely. Consider the arithmetic problem. What's 2 cubed meaning 2 times 2 times 2? It's 8. Of course. What about 2.001 times 2.001 times 2.001? Slightly more than 8? Sure, but how much more? What we are what we are after here is a way of thinking, not a numerical answer. The general question is, what when we change the input to a problem here by changing to 2.001, how much does the output change? Here it changes from 8 to 8 plus something whose answer we want to understand. Since it's hard to resist picking, let's go ahead and see what a calculator has to say. Punching in 2.001 and hitting the execute button gives 2.001 raised 3 equal 2.001 cube equals 8.012006001. The structure to notice is that the extra bit after the decimal point is really the extra bits of very different sizes. Think of this as small plus super small plus super small. We can understand the structure we're seeing by working with algebra. Suppose a quantity x, played here by the number 2, change slightly to x plus x. In this case become 2.001. The symbol delta x denotes the difference is x, meaning a tiny change in x. Here delta x equal 0.001. Then when we ask that 2.001 cube is, we are really asking what x plus delta x cube is. Multiplying it out or using Pascal's triangle or binomial theorem, we find that for our problem where x equal to this equation becomes. Now we see why the extra bit beyond 8 consists of 3 bits of different sizes. The small but dominant bit is 12 delta x equals 12 times 0.001 equals 0.021. The remaining bits the remaining bits 6 delta x squared and delta x cubed account the super small 0.00 the super small and the super small. The more factors of delta x there are in a bit, the smaller it is. That's why the bits are graded in size. Every additional multiplication by the tiny factor delta x
makes a small bit even smaller. The key insight behind differential calculus is displayed right here in this humble example. In many problems of cause and effect, thus and response, input and output, or any other sort of relationship between a variable x and another variable y that depends on it, a small change in the input, delta x, produces a small change in the output, delta y. The small change is typically organized in a structure what we can exploit. Namely, the change in the output consists of a hierarchy of bits. They are graded in size from small to super small to even smaller contributions. That gradation allows us to focus on the small but dominant change and neglect all the rest, the super small and even smaller one. That's the key insight. Although the small change is small, it is gigantic compared to the others, much like point or point 021 was gigantic compared to n. Differentials. This way of thinking in which we neglect all contributions to the right answer except for the biggest one, the lion's share, might seem only approximate, and it is if the change in the input like 0.001 we take onto the two above are finite changes. But if we consider infinitesimal changes in the input, then our thinking becomes exact. We make no error whatsoever. The lion's share become the lion's share become everything. And as we've seen throughout this book, infinitesimal changes are precisely what we need to make sense of slopes, instantaneous velocities, and the areas of curved regions. To see how this works in practice, let's go back to the example above where we were trying to calculate the cube of a number slightly greater than 2. Except now, let's change 2 to 2 plus dx when the x is supposed to represent an infinitesimally small difference delta x. This notion is inherently nonsensical, so don't think about it too hard. The point is that learning how to work with it makes calculus a breeze. In particular, in the early calculation of 2 plus delta x cubed as 8 plus 12 delta x plus 6 delta x squared plus delta x cubed now shrinks to something much simpler. What happened to the other terms like 6, 6 delta x squared plus delta x cubed? We discarded them. They are negligible. They are super small and super small infinitesimals and utterly inconsequential compared to 12 delta x. But they but then why do we keep 12 delta x? Isn't it equally negligible compared to 8? It is, but if we will discard it too, we would not be considering any change at all. Our answer would be frozen at 8. So the recipe is to study infinitesimal change, keep terms in fourth dx to the first power and ignore the rest. This way of thinking using infinitesimals like delta x can rephrase in terms of limits and make perfectly kosher and rigorous. That's how modern textbooks deal with them. but it's easier and faster to use infinitesimals. The term of art for them is in this context is differentials. Their name comes from thinking of them as being like the differences delta x and delta y. In the limit as those differences tend to zero, they are like what we saw when we look at a parabola under a microscope and watch the curve get straighter and straighter as we zoom it on it. Derivatives via differentials. Let me show you how easy certain ideas become when couched in differentials. For example, was the slope of a curve when it's viewed as a graph in the xy plane, as we learned from our book with the parabola in chapter 6. The slope is derivative of y defined as the limit of delta x or delta y over delta x as delta x approaches 0. But what is it in terms of differentials? It's simply delta y dy dx. It's a curve. It's as if the curve is made up of straight state physics. It's it's as if the curve is made up of little straight pieces. If we think of delta y dy as an infinitesimal rise and infinitesimal rise and delta x as an infinitesimal run, the slope is simply the rise over over the run, but as it always is, and hence is the dy dx. To apply this approach to a specific curve, say y equals x cubed, the case we consider while cubing numbers slightly greater than 2, we calculate delta dy as follows. Write y plus dy equals x plus the x cubed. As before, the right hand side expands to x plus delta x equals x cubed plus 3x squared dx plus dx delta x squared plus the x cubed. But now, following the receipt, we discard the terms dx squared and dx cubed since they are not part of the lion's share. Thus, y plus dy equals x plus the x cubed equals x cubed plus the 3x squared dx. And since y equals x cubed, we can simplify the equation above to obtain dy equals 3x squared dx. Dividing both sides by dx yields the corresponding slope. Dy dx equals 3x squared. At x equals 2, this gives a slope of 3 to square equals 12. That's the same 12 we saw earlier. It's why changing 2 to 2.001 gave us. It means that an infinitesimal change in x near 2, call it dx, gets converted to an infinitesimal change in y near 8, call it dy, that's 12 times bigger. Dy equals 12 dx. Incidentally, similar reasoning shows that for any positive integer n, the derivative of y equals x to the raised n is dy dx equals n x raised n minus 1. A result we've mentioned earlier. With a little more work, we could extend this result to negative, fractional, and irrational n. This great advantage of infinitesimals in general and differentials in particular is that they make calculations easier. They provide shortcuts. They free the mind for more imaginative thought, just as algebra did for geometry in an earlier era. This is what Leibniz adored about his differentials. As he wrote to his mentor Huygens, "My calculus gave me almost without meditation. The great part of the discoveries which have been made concerning this subject, for for what I love most about my calculus is that it gives us the same advantages over the ancients in geometry of Archimedes that Viet and Descartes have given us in the geometry of Euclid and of Apollonius, in freeing us from having to work with the imagination. The only thing wrong with infinitesimals is that they don't exist, at least not within the system of real numbers. Oh, and one other thing, they are paradoxical. They would not make sense even if they did exist. One of Leibniz's disciples, Johann Bernoulli, realized they have to satisfy nonsensical equations like x plus dx equals x, even though dx isn't zero. He- hmm. Well, you can't have everything. Infinitesimals do give the right answers once we learn how to work with them, and the benefits they provide more than make up for any physical distress or that they may cause. There are Picasso's lie that helps us realize the truth. As a further demonstration of infinitesimals power, Leibniz used Leibniz used them to the Snell-Stein law for the refraction of light. Recall from chapter 4 that when light passes from one medium in another, let's say from air into water, it bends in accordance with a mathematical law that was discovered and rediscovered several times over the centuries. Fermat had explained it with his principle of least time, but the struggle mightily to solve the optimization problem that his principle implied. With his new calculus of differentials, Leibniz reduced the sine law with ease and noted with evident pride that other very learned men have shown in many diffuse ways that what someone first in this calculus can accomplish in these lines as by magic. The fundamental theorem via differentials. Another triumph of Leibniz's differentials is that they made the fundamental theorem transparent. Recall, the, recall, the, recall that the fundamental theorem concerns the area accumulation function Ax, which gives the area under the curve y equals fx over the interval 0 to x. The theorem says that as we slide x to the right, the area under the curve accumulates at a rate given by fx itself. Thus, fx is the derivative of ax. To see where this result comes from, suppose we change x by an infinitesimal amount to x plus dx. How much does the area ax change? By definition, it changes by an amount dA. Hence, the new area equals the old area plus the change in area and is therefore A plus dA. The fundamental theorem drops out immediately once we visualize what dA must be. As suggested by the picture below, the area changes by the infinitesimal amount dA given by the area of the infinitesimally thin vertical strip between x and x plus dx. The strip is a rectangle of height y and base dx, so its area is its height times its base, which is y dx, or if you prefer x fx dx. Actually, the strip is a rectangle, only few infinitesimally in reality. For a strip of any infinite width dx delta x, the change in area delta A has two contributions. The dominant the dominant one is a rectangle of area y delta x, A much smaller one is the area of the tiny, curved, triangular-looking cap on top of the rectangle. Here's another case when the infinitesimal world is nicer than the real world. In the real world, we would have to account for the area on the cap, which which wouldn't be easy to estimate because it would depend on the details on the curve on top. But as the width of the rectangle approaches zero and becomes dx, the area of the cap becomes negligible compared to the area of the rectangle. It's super small compared to a small. The upshot is that dA equals y dx equals fx dx. Boom! That's the fundamental theorem of calculus, or as it is more politely phrased nowadays, in our misguided era when differentials have been forsaken for derivatives. This is exactly what we found in chapter 7 with the pen roller argument. One last thing, when we regard the area under a curve as a sum of infinitely many infinitesimal rectangular strips, we write it as that long neck swan-like symbol is actually stretched out as. The S reminds us that a summation is taking place. It's a summation of a peculiar kind, distinctive to integral calculus, involving a sum of infinitely many infinitesimal strips, all being integrated into a single coherent area. As a symbol of integration, it's called an integral sign. Leibniz introduced it in 1677 manuscript and published it in 1686. Its, calculus' most recognizable icon, the zero at the bottom of it and the x at the top of it, indicate the endpoints of the interval of the x-axis over the rectangle stand. Those endpoints are called the limits of integration. What led Leibniz to differentials and the fundamental theorem? Newton and Leibniz arrived at the fundamental theorem of calculus by two separate routes. Newton came at it by thinking about motion and flow by continuous side of math. Leibniz came at it from the other side. Although he was not a mathematician by training, earlier in his life he'd spent some time thinking about discrete math, whole number and counting, combinations and permutations and fractions and sums of a particular sort. He began wading into deeper waters after he met Christian Huygens. At the time, Leibniz was serving on a diplomatic mission in Paris, but he found himself entranced by what Huygens was telling him about the latest developments in the mathematics, and he wanted to learn more. With amazing pedagogical prescience, or what is like, Huygens challenged his student with a problem that led him to fundamental theorem. The problem he gave him was to calculate this infinite sum. The dots in the denominators and the dots in the denominators mean multiplication. To bring the problem down to earth, let's begin with a warm-up version. Suppose the sum was, say, 99 terms in it instead of infinitely many. Then we would have to calculate. If you don't see the trick, this is a tedious but straightforward calculation. With sufficient patience, of a computer, we could ploddingly add up with the 99 fractions. But that would be missing the point. The point is to find an elegant solutions. I failed in math in part because they are pretty, but also but they are pretty, but also because they're beautiful. They are powerful. The light they see can often be used to illuminate other problems. In this case, the elegant light that Leibniz discovered quickly pointed him to the fundamental theorem. He solved Huygens' problem with a brilliant trick. The first I saw it, I felt like it was I, I felt like I was watching a magician pull a rabbit out of a hat. If you want to experience the same feeling, skip the analogy I'm about to present. If you would prefer to understand what's behind the magic, here's what makes it work. Imagine some climbing a very long and irregular staircase. Suppose our climber wanted to measure the total vertical rise from the bottom of the staircase to the top. How could he do that? Well, he could always add up all the rises of the individual steps in between. The, uns- the That uninspired strategy would be like adding up the 99 facts in the sum as before, in the sum as above. It could be done, but it would be unpleasant because the staircase is so irregular, and if the staircase has millions of steps, adding up all the rises would be a hopeless task. There has to be a better way. The better way is to use an altimeter. An altimeter is a device that measures altitude. If Zeno in this picture had an altimeter, he could solve his problem by subtracting the altitude at the bottom of the staircase from the altitude at the top. That's all there is to it. The total vertical rise equals the difference in two altitudes. The difference between them has to equal the sum of all the traces in between. No matter how irregular the staircase is, the trick will always work. The success of the trick hinges on the fact that the altimeter readings are intimately related to the rise of the steps. The rise of any given step is the indifference of consecutive altimeter readings. In other words, the heading of a step equals the altitude at this equals the altitude at its top minus the altitude at its bottom. By now, you're probably thinking, what does an altimeter have to do with the original math problem of adding up a long list of complicated irregular numbers? Well, if we could somehow find the analog of an altimeter for a complicated irregular sum, that sum would become easy. It would just add up to the difference between the highest and lowest altimeter readings. This is essentially what Leibniz did. He found an altimeter for the sum x. It enabled him to write each term in the sum as a difference of consecutive altimeter readings, in which in turn allowed him to compute the desired sum using the idea mentioned above. Then he generalized his altimeter to other problems. Ultimately, it led him to the fundamental theorem of calculus. With this analogy in mind, let's examine S. We're going to rewrite each term as a difference of two other numbers. This is like saying that the rise of each step is the difference of altimeter readings at its top and bottom. For the first step, the writing goes like this. Admittedly, it's not obvious yet where this is going, but stay tuned. In a moment, we'll see how helpful it is to rewrite the expression 1 times 2 as a difference of two consecutive unit factors fractions 1 over 1 and 1 over 2. A unit fraction a unit fraction means a fraction with a 1 in the numerator. These consecutive these consecutive unit fractions are going to play the role of consecutive altimeter readings. Also, if the arithmetic above seems unclear, try simplifying the equations by working them from right to left. On the far right, we are subtracting the unit factor 1 over 2 from another unit fraction 1 over 1. In the middle, we are putting them of a common denominator, and on the far left we are simplifying the numerator. Similarly, we can rewrite each other term in S as a difference of consecutive fractions, and so on. When we add up all these differences of unit fractions, S becomes. Now we see the method in the madness. Look carefully at the structure of this sum. Nearly all the unit fractions appear twice, once with a negative sign and once with a positive sign. For example, 1 over 2 is subtracted and then add up again, then the net effect is that 1 over 2 times cancel each other out. The same is true for 1 over 3. It occurs twice and cancels itself. Nearly all the other fractions up to and including 1 over 99 do the same. The only exceptions are the first and last unit fractions, 1 over 1 and 1 over 100, being at the ends of the line in S. They have no partners to cancel with. After the smoke clears, they are the only unit fractions left standing, so the result is. This makes perfect sense in terms of the staircase analogy. It says the total rise of all a step is the altitude of the at the top of the staircase minus the altitude at the bottom. Incidentally, S simplifies to 99 over 100. That's the answer to the puzzle with 99 terms. Leibniz realized that he could add any number of terms using the same trick. If the sum had n terms instead of 99, the result would be. Thus the answer to Huygens' original equation about the infinite sum becomes clear. As n approaches infinity, the term 1 over n plus 1 approaches 0, and so approaches 1. The limiting value of 1 is the answer to Huygens' puzzle. The key that allowed Leibniz to find the sum was that it had a very particular structure. It could be rewritten as a sum of consecutive differences. In this case, difference of consecutive unit fractions. The difference structure caused the massive cancellation we saw above. Some with this property are now a term telescoping sums because they call to mind one of those all collapsible telescopes you see in pirate movies, the kind of spyglass that can be stretched out or contracted at will. The analogy is that the original sum appears in its stretched out form, but because of its different structure, it can be telescoped down to a much more compact result. The only terms that survive the collapse are the terms without partners to cancel them, the ones at the very ends of the telescope. Naturally, Leibniz wondered if he could use the telescoping trick or other problems. It was an idea worth pursuing, given how powerful it could be. Confronted with a long list of numbers to sum, he could write each number as a difference of consecutive numbers to determine the telescoping trick would work again. And that got Leibniz thinking about areas. Approximating the area under a curve in the xy plane, after all, amounted to summing a long list of numbers, the area of lots of thin vertical rectangular strips. The idea behind what he had in mind is demonstrated in the figure above. It shows how it shows only 8 rectangular areas, but you should try to imagine a similar image with million or billion of much thinner rectangular rectangles, or better yet, infinitely many infinitesimally thin rectangles that unfortunately is hard to draw or visualize. That's why I'm using egg blocky rectangles for now. For simplicity, suppose all the rectangles have the same width. Call it the delta x. The heights of the rectangles are y1, y1, y2 until y8. Then the total area of the approximated rectangles is the sum of egg numbers would conveniently telescope if we could some will find magic number a0 until a8 whose differences give the rectangular areas, and so on down to y8 delta x equals a8 minus a7. Then the total area of the rectangles would telescope to this. Now, think about the limit of infinitesimally thin strips. Their width delta x turns into the differential dx. Their varying heights y1, y2 until y8 become yx, a function that gives the height of the rectangle standing over the point labeled by variable x. The sum of infinitesimally many rectangular areas becomes their integral, and as from the earlier telescoping, the sum that was previously a8 minus a0 now becomes ab minus aa, where a and b are the values of x on the left and right ends of the area behind calculated. The infinitesimal version of telescoping then yield the exact area under the curve. And how do we find the magic function ax that making all this possible? Well, we look at the earlier equation like y1 delta x equals a1 minus a0. They morph into as the rectangles become infinitesimally thin. To put the same result in terms of derivatives instead of differentials, divide both sides of the equation above by dx to get. This is how we find the analogues of the magic numbers a0, a1 until a8 that cause telescoping to occur. In the limit of infinitesimally thin strips, they are given by the unknown function ax whose derivative is the given curve yx. All of this is the Leibniz version of the backward problem and the fundamental theorem of calculus. As he put it, finding the areas of figures is reduced to this. Given a series, to find the sums, or to explain this better, given a series to find another one whose differences coincide with the terms of the given series. In this way, differences and telescoping sums guided Leibniz to the differentials and the integrals, and from there to the fundamental theorem, just as flexions and expanding areas had led Newton to that same secret fountain. Fighting HIV with an assist from calculus. Although differentials are fictions of the mind, they have affected our world, our societies, and our lives in profoundly non-fictional ways, ever since Leibniz invented them. For an example in our own time, consider the supporting role that differentials played in the understanding and treatment of HIV, the human immunodeficiency virus. In 1980s, a mysterious disease began killing tens of thousands of people a year in the United States and hundreds of thousands worldwide. No one knew what it was, where it came from, or what was causing it, but its effects were clear. It weakened patients' immune systems so severely that they become vulnerable to rare kinds of cancer, pneumonia, and opportunistic infections. Death from the disease was slow, painful, and disfiguring. Doctors named it acquired immunodeficiency syndrome or AIDS. Patients and doctors were desperate. No cure what was inside. Base research demonstrated that retrovirus was the culprit. Its mechanism was insidious. The virus attacked and infected white blood cells called called helper T called helper T cells, a key component of the immune system. Once inside, the virus hijacked the cell genetic machinery and co-opted it into making more viruses. Those new virus particles then escape from the cell, hitch a ride in the bloodstream and other bodily fluids, and look for more T cells to infect. The body's immune system responded to this invasion by trying to flush out the virus particles from the blood and kill as many infected T cells as it could find. In so in so doing, the immune system was killing an important part of itself. The first antiretroviral drug approved to treat HIV appeared in 1987. Although it slowed HIV down by interfering with the hijacking process, it was not as effective as hoped, and the virus often became resistant to it. A different class of drugs, called protease inhibitors, appeared in 1994. They thwart HIV by interfering with the newly produced virus particles, keeping them from maturing and rendering them non-infectious. Although also not a cure, protease inhibitors were a godsend. Soon after protease inhibitors became available, a team of researchers led by Dr. David Ho, a former physics major at Caltech, and so presumably someone comfortable with calculus, and a mathematical immunologist named Alan Parelson collaborated on a study that changed how doctors to about thought about HIV and revolutioned how they treated how they treated it. Before the work of Ho and Parelson, it was known that untreated HIV infection typically progressed to three stages. In a good primary stage of a few weeks, a chronic of paradoxically asymptomatic stage of up to 10 years, and a terminal stage of AIDS. In the first in the first stage, soon after a person becomes infected with HIV, he or she displays flu-like symptoms of fever, rash, head and headaches, and a number of helper and a, and a number of helper T cells, also known as CD4 cells, in the bloodstream plummets. A normal T cell count is about 1000 cells per cubic millimeter of blood. After primary HIV infection, T cell count drops to the low hundreds. Since T cells help the body fight infections, the, the depletion severely weakens the immune system. Meanwhile, the number of virus particles in the blood, known as the viral blood as the viral load, spikes and then drops as the immune system begins to combat the HIV infection. The flu-like symptoms disappear and the patient feels better. At the end of this first stage, the viral load stabilizes at a level that can puzzlingly last for many years. Doctors refer to this level as the set point. A patient who is untreated may survive for a decade with no HIV-related symptoms and no lab findings other than a persistent viral load and a low and slowly declining T cell count. Eventually, however, the asymptomatic stage ends and age sets in, marked by a further decrease in the T cells count and a sharp rise in the viral load. Once an, an untreated patient has full-blown AIDS, opportunistic infections, cancers, and other complications usually cause the patient's death within 2 or 3 years. The key to the mystery was in the decade-long asymptomatic stage. What was going on then? HIV lying dormant in the body. Other viruses were known to hibernate like that. The genital herpes virus, for example, hunkers down in nerve ganglia to invade the immune system. The chickenpox virus also does this, hiding out in the nerve cells for years and sometimes awakening to cause shingles. For HIV, the reason for the latency was unknown, but it became clear after Ho and Perelson's work in a 1995 they in a 1995 study. They gave patients a protease inhibitor not as a treatment but as a probe. This nudged a patient's body off its set point and allowed her and Perelson for the first time ever to track the dynamics of the immune system as it battled HIV. They found that after each patient took the protease inhibitor, the number of virus particles in his bloodstream dropped exponentially fast. The rate of decay was incredible. Half of the virus particles in the bloodstream were cleared by the immune system every 2 days. Differential calculus enabled Perelson and Ho to model this exponential decay and extract its surprising implications. First, they represent First, they represented the changing concentration of virus in the blood as an unknown function Vd, where T denotes the elapsed time since the protease inhibitor was administered. Then they hypothesized how much the concentration of virus would change dV in an infinitesimally short time interval dt. Their data indicated that a constant fraction of the virus in the bloodstream was cleared each day, so perhaps the same constancy would hold when extrapolated down to an infinitesimal time interval dt, since dy over v is the fractional change in the virus concentration. Their model could be translated into symbols as the following equation. Here, the constant of proportionality, C, is the clearance rate, a measure of how fast the body flushes out the virus. The equation above is an example of the differential equation. It relates the differential dv to v itself and to the differential t of the elapsed time. By using the fundamental theorem to integrate both sides of the equation, Parallelson and Ho solved for Vt and found it satisfied, where V0 is the initial viral load and Ln denotes the natural logarithm, the same logarithm function that Newton and Mercator studied in 1660s. Inverting this function then implied where e is the base of the natural logarithm, thus confirming that the viral load did indeed decay exponentially fast in the model. Finally, by fitting an exponential decay curve to their experimental data, Ho and Parallelson estimated the previously unknown value of the clearance rate of C. For those who prefer derivatives to differentials, the model equation can be rewritten as: here, dv dt is the derivative of v. It measures how fast the virus concentration grows or declines. Positive values of the derivative signify growth, negative values indicate decline. Since the concentration V is positive, the minus CV must be negative, so the derivative must also be negative. Which means the virus concentration must decline, as we know it does in the experiment. Furthermore, the proportionality between dv dt and v means that the closer v gets to zero, the more slowly it declines. Intuitively, the slowing decline of V is like what happens if you fill a sink with water and then allow it to drain. The less water there is in the sink, the more slowly it flows out because there's less water pressure pushing it down. In this analogy, the amount of virus is like the water and the draining is like the outflow of the virus due to its clearance by the immune system. Having modeled the effect of the protease inhibitor, Parallelson and Ho modified their equation to describe the conditions before the drug was administered. They assumed the equation would become in this equation P refers to the uninhibited rate of production of new virus particles. Another crucial unknown at the time, Parallelson and Ho imagined that before administration of the protease inhibitor, at every moment infected cells were releasing new infectious virus particles, which then infected other cells, and so on. This potential for a raging fire is what makes HIV so devastating. In the asymptomatic phase, however, there is evidently a balance between the production of the virus and its clearance by the immune system. At the set point, the virus is produced as fast as it's cleared. That gave new insight into why the viral load could stay the same for years. In the water in the sink analogy, it's like what happens if you turn on the faucet and open the drain at the same time. The water would reach a steady state level at which outflow equals inflow. At the set point, the concentration of virus doesn't change, so its derivative must be zero. dv dt equals zero. Hence, the steady state viral load V0 satisfies P equals C V0. Parallelson and Ho use this simple equation P equals CV0 to estimate a vitality important number that no one had found a way to measure before. The number of the number of virus particles being cleared each day by the immune system. It turned out to be 1 billion virus particles a day. The number was unexpected and truly stunning. It indicates that a titanic struggle was taking place during the seemingly calm 10 years of the asymptomatic phase in a patient's body. Every day, the immune system cleared 1 billion virus particles and the infected cells released 1 billion new ones. The immune system was in a furious, all-out war with the virus and fighting into a near standstill. Ho, Perelson and the college conducted a follow-up study in 1996 to get a better handle on something that had been in 1995 but couldn't resolve back then. This time, they collected viral load data at shorter time intervals after the protease inhibitor was administered because they wanted to obtain more information about an initial lag they could observe in the medicine's absorption, distribution, and penetration into the target cells. As the drug was given, the team measured the patient's viral blood every 2 hours until the 6 hours, then every 6 hours until day 2, and then once day 4 until a 7. One on on the mathematical side, Perelson refined the differential equation model to account for the lag and to the dynamics of another important variable, the changing number of infected T cells, where the researchers redid the experiment, feed the data to the model's predictions, and estimate its parameter again. They obtained results even more staggering than before. 10 billion virus particles were being produced and then killed from the bloodstream each day. Moreover, they found that infected T cells had a lifespan of only about 2 days. The size surprisingly short lifespan added another piece to the puzzle, given that T cell depletion is the hallmark of the HIV infection and AIDS. The discovery that HIV replication was so astonishingly rapid changed the way the doctor treated their HIV for positive patients. Until the work of Ho and Perelson, the physicians waited until HIV emerged from its supposed hibernation before they prescribed antiviral drugs. The idea was to conserve forces until the patient's immune system really needed help because the virus often become resistant to the drugs and then there being nothing else to try. So it was generally thought wiser to work with until patients were for long in their illness. Ho and Perelson's work turned this picture upside down. There was no hibernation. HIV and the body were locked in the pitch struggle every second of every day, and the immune system needed all the help it could get as soon as possible af- after the critical early days of infection. And now it was obviously why no single medication worked for very long. The virus replicated so rapidly and mutated so quickly it could find a way to escape almost any therapeutic drug. Parelson's mathematics gave a quantitative estimate of how many drugs had to be used in combination to beat HIV down and keep it down. By taking the account of the measured mutation rate of HIV, the size of its genome, and the newly estimated number of virus particles, that were produced daily. He demonstrated mathematically that HIV was generating every possible mutation at every base in its genome many times a day. Since even a single mutation could confer drug resistance, there was little hope of success with single drug therapy. Two drugs given at the same time would stand a better chance of working, but Pearson's calculations showed that a sizable fraction of all mu- possible double mutations also occurred each day. These drugs in combination, however, would be hard for the HIV virus to overcome. The math suggested that the odds were something like 10 million to 1 against HIV being able to undergo the necessary three simultaneous mutations to escape triple combinations therapy. When Ho, in college, tested a three drugs cocktail on HIV infected patients in clinical studies, the results were remarkable. The level of virus in the blood dropped out of 100-fold in 2 weeks. Over the next month, it became undetectable. This is not to say that HIV was eradicated. Studies soon afterward showed the virus could rebound aggressively if patients took a break from therapy. The problem is that HIV can hide out in various places in the body. It can lie low in sanctuary sites that the drugs cannot readily penetrate or lack in latently infected cells and rest without replicating, a sneaky way of evading treatment. At any time, these dormant cells can wake up and start making new viruses. That's why it's so important for HIV positive people to keep taking their meds even when their viral loads are low or undetectable. Still, even though it did not cure HIV, triple combination therapy changed it to a chronic condition that could be managed, at least for those who had access to treatment. It gave hope where almost none had existed before. In 1996, Dr. David Ho was named Time Magazine Man of the Year. In 2017, Alan Perelson received a major prize for his profound contributions to theoretical immunology, which bring insight and save lives. He is still using calculus and differential equations to analyze viral dynamics. His latest work concerns hepatitis C, a virus that affects about 170 million people worldwide and kills about 350 350,000 people each year. It is the leading cause of the cirrhosis and liver cancer. In 2014, with the help of Pearson's math, new treatments for hepatitis C were developed that are safe and easy to take as was a pill day. Incredibly, the, the treatment cures the infection in nearly every patient.